this will mute it. So right now it's on. To mute, you press that. Yeah. And it should be working a bit. Yeah. Is this?
All right. Hello. It's 11, so I suggest we get started on the second session of talks of the day. I'll be chairing the session. My name is Casper, and giving this talk is Jihi Park, who'll be telling us about semantic transformations.
Thank you. Hello, I'm Ji Park, and today I will present about our work, Semantic Transformation Framework for Rewriting Rules. This work is done with Jae-min Hong and Seok-young Yu at KAIST. Rewriting rule-based program transformation describes program transformation as the rule which specifies to which program part of which part of the program should be replaced to each part. Because of its simplicity, it is useful for automatic verification of transformation components or synthesizing the program transformation. And the rewriting rule consists of match and substitution primitives. The match means the syntactic and semantic condition of the target component, and the substitution means the replaced component. The static analysis is mostly used to specify the semantic condition of the match part. It also defines semantics preservation property, which means the original program and transformed program is related with some formula. Because there are many frameworks with different formulation, it is difficult to analyze and compare each framework's set of expressible transformations. So more specifically, the transformation framework has difference in the match, substitution, and semantic preservation. To specify match, some frameworks support to write the semantic condition with computation tree logic, such as logical formula with quantifiers over time and computation path information. On the other side, other frameworks can support first-order logic formula, such as with analysis, a predefined analysis as the predicate, and also another framework can support to users make their desired data flow analysis freely. There are also differences in to specify substitution. Some frameworks supports only to replace a single node in control flow graph, while others can support replacing multiple nodes in control flow graph, or more generally, the substitution in the abstract syntax tree level. There are also differences in the semantics preservation property for each framework. Some of it define it as equivalence on the notational semantics, which means the input state, when the same inputs are given, then the output states of the original program and transform program should be equal. And some other framework can define it as a simulation relation between program states. In simulation relation, the two states are not must to be exactly equal, but it satisfies a relation which preserved after a single step over for both original and transformed program. To express the transformation uniform and systematic way, Kujo and Kujo propose a semantic transformation framework. It is a unifying framework that explains transformation and its semantics preservation property with abstract interpretation. It introduces semantic transformation to explain both syntactic transformation and semantics preservation. In this framework, syntactic transformation is considered as an over-approximation of semantic transformation, and semantics preservation is considered as an equality on some abstraction of the semantics, which is called the observational abstraction. Here is the diagram of the semantics transformation framework. Given a program, first, the syntactic transformation with the static analysis result transforms program to another program. And on the other side, the semantic transformation transforms the semantics of the original program to make transformed semantics. Then the semantics preservation is now, to show the semantics preservation of the concrete transformation, it is now divided into two parts. First, one should show the semantics of the transformation from the program is equal to the transformed semantics of the original program. And second, they should show the observational abstraction of the original program semantics are equivalent to the transformed semantics. Although it can express general transformations, there is a still gap from the framework to concrete transformations. Although some example transformations are formulated in semantics transformation framework, but generally it does not have guidelines to prove the syntactic and semantic equivalence on the transformation. Also, the semantic transformation framework does not have mature part, which commonly exists in rewriting rule-based program transformation. So the structure of the rewriting rule-based transformation and semantic transformation is different. So it is hard to correspond the component of the semantic rewriting rule to semantic transformation framework. Sorry. To solve this issue, we define a semantic transformation framework tailored to rewriting rules, and we provide syntax-directed guidelines to prove syntactic semantic equivalence. And also, we further present theorems that simplify proofs by identifying properties of transformation, and we define 6 well-known program transformations to show feasibility of our work. First, I will show how our semantic transformation frameworks are defined and how we provide the syntax-directed guidelines. The target transformation of our framework is the rewriting rule-based program transformation, which have match and substitute primitives. And also, our target transformation is based on semantic transformation, which means the transformed program's semantic, which is execution trace, should depend on only original program's execution trace and the program analysis result. So if we think about the transformation which replaces arbitrary expression to arbitrary value without any analysis, it is not in our interest because the transformed program's execution trace is not dependent on original program's execution trace. It is just arbitrary. To show our work, so we define a target language. It is just a simple imperative language with while and loop and branch statement, and it has just the integer and boolean values. We define the semantics of the program as the trace semantics. This is the example program, and the trace of the given program is given as follows. The trace is an ordered collection of the information, ordered collection of the event during the execution of the program. More specifically, trace is defined as the sequence of program label and the action. Action means the action describes what effect on the program what effect on the execution of the statement and how the execution of statement affect to overall program. So, for example, when the program executes the statement, assignment statement, then the action records assignment action, which consists of assigned variable and the expression, which is in the assignment expression, and the evaluation of the expression on that execution. Similarly, when the program executes the branch or loop condition, then it records the evaluation of the condition. Now we show high-level overview of our approach. It consists of 4 parts: matcher, syntactic substitutor, semantic substitutor, and the correctness argument. The matcher matches program with target statement and whole program static analysis result. And it produces output which is needed to syntactic and semantic substitutors. Now we will show our component with the example transformation, the constant propagation transformation. So the matcher needs a program component and the analysis result. For constant propagation transformation, the required analysis is value analysis of each variable. So the analysis returns the possible values at the label. And the matcher of constant propagation matches the statement when the target statement is the assignment expression or assignment statement of the variable expression, and the target variable has only constant possible value. Then it returns the triple consists of the matched label and assigned variable and the constant value. So in this example, the matcher matches the label 8 to produce a triple 8 consists of 8, y, and 2. And after the matcher matches the target component, the syntactic substitutor specifies how to replace the match statement. It generates transformed statement from match statement and matcher output. So for our example, the syntactic substitutor is using the matcher output to produce assignment statement of constant expression. So in this case, the matcher matches to label 8 and produces y assigned to 2. Note that the original program and transformed program is different only for the matched part, and other parts remain the same. And semantic substitutor, on the other side, semantic substitutor specifies the effect on program trace. Regardless of the syntax, it generates transformed trace from the program trace of original program and the matcher output. The semantic substitutor for constant propagation is defined as follows. It replaces only for action which passes the matched label, and it changes the action of the matched label into only for the expression part. It changes the expression part to constant expression. So when the original trace have the action of some unknown expression, then it replaces the expression to the constant expression. So in the constant propagation transformation, the semantic substitution only changes the action of the matched label, but for more complicated transformation, the semantic substitutor can also delete or insert new actions in the trace. After defining matcher, syntactic, and semantic substitutor, we should show how the syntactic transformation and semantic transformation are equivalent. So we call it as correctness argument, and it states that semantics of transformed program is equal to transformed semantics of original program only when the matcher produces a valid matcher output. So this equivalent is up to the matcher output. We propose the syntax-directed proof for rewriting rule-based transformation, which is the main difference of previous semantic transformation framework and ours. We divide the correctness argument into 2 parts. First is base case, and second is inductive case. The base case carries proof for the equivalence for only the matched part, and it ignores the surrounding part of syntax. On the other side, the inductive case provides the proof for surrounding part of the syntax. So I will show the correctness argument with the examples. First, the base case relates syntactic and semantic transformation when the whole program is matched. So in this example, the original program y assigned to x and transformed program y assigned to 2 is equivalent up to the matcher output 8, y, and 2. To more specific, the definition of correctness argument is defined as follows. when the original program is transformed with syntactic substitution with the mature output, then it produces transformed program. And for a trace which have the original program cement trace as a subpart, then it is transformed with semantic substitution with the mature output. Note that the important thing is that the original trace have the trace should satisfy the mature output. It means in this case, the value of x at the end of T1 should be 2 to satisfy the mature output. In this restriction, the correctness argument is the proof of the equivalence between the transformed trace and the transformed program trace. So after the base case, the inductive case proves the correctness argument for the component surrounded by context. Context means the statement with whole, which will be filled with two components, which will satisfy correctness argument. So in our language, there are 5 kinds of whole. So we should show the inductive case for all 5 cases. Suppose we prove base case and inductive case for all contexts for constant propagation transformation, then I will show how the correctness argument of arbitrary program is proved. So first, the base case carries proof only for matched part, and after using induction for the sequence statement, then the correctness argument is propagated to a larger program component. And next, using induction again for branch context, then the correctness argument is propagated to more larger program component. And after repeatedly applying this induction for appropriate context, we can prove the correctness argument for any two program which is the result of the syntactic substitution. The advantage of the separation of base case and inductive case is that for base case, we just consider the matched part, and we can ignore the surrounding part with the assumption of the valid mature output of trace. And in contrast, for inductive case, we can ignore the inner component of the syntax, and just we can use the fact that inner components are related by correctness argument. So we exploit this fact to reduce more burden of users of proving inductive case. I will show it later. And yes. So we provide the syntax-directed guidelines to prove, but there is still a burden to user to prove correctness argument for base case and all inductive cases. So we present theorems that simplify proofs by identifying properties of transformation, and we define 6 well-known program transformation to show feasibility of our work. So there are some example properties of semantic substitutor. First is concatenation preservation, which means the substitution of 2 concatenated traces is equal to concatenation of substituted traces. And second, control flow preservation means that substitution of branch, loop, or sequence section is preserved. And next, final state preservation means that for any trace, the value of the variables in the end of the trace is equal to value of variables in the substituted trace. Using the properties of these kind of analysis, syntactic and semantic substitutor, we introduce theorems to prove induction for some contexts. For example, when the semantic substitutor satisfies concatenation, control flow, and final state preservation, we have free induction theorem for free induction cases for loop context. Similar to this, we introduce 5 theorems which require some properties of the component of transformation. more details are in the paper. And we define to show out the feasibility of our work, we should define the transformation component of 6 well-known program transformations and define and prove the correctness argument for these 6 kinds of transformation. For all 6 transformation, we define the base case manually. We prove the base case manually, but for inductive case, we just prove it manually for only data assignment elimination transformation. And for all other 5 transformation, we use the properties of the transformation to show the inductive case to eliminate to show inductive case using theorems. So to summarize, we propose a semantic transformation framework which is tailored to rewriting rule, and we show syntax-directed correctness argument to show to provide a guideline to prove correctness argument. And to further reduce the burden of the user, we introduce the theorems to reduce the theorems to show inductive cases for some context, and we define 6 example transformations in our framework to show feasibility of our work. Yeah. Thank you for listening and welcome question.
Thank you for an intriguing talk. So in the compiler verification literature, there has been some attempts to verify the compiler correctness using some compositional concept of simulation relations. So would you please compare this somehow modular or compositional simulation approaches to your approach?
Oh, thank you for a great question. Simulation relation, the difference of the simulation relation and ours is that in simulation relation, the states should be matched exactly, but in our semantic transformation framework, the exact correspondence or preserved after fixed step of time. Our trace does not have this kind of strict regulation of the correspondence. We just need to define which trace will be replaced to which path, which trace, and I think it is the more general to simulation relation. And there is also similarity with the simulation relation and ours, because the simulation relation also satisfies the original state, correspond original state to transformed state, and our semantic transformation framework has original trace to place the transformed trace. Yes.
More questions? So you proved you implemented 6 different program transformations. Were any of those transformations the same as Cousseau's? I mean, you're taking the framework of Cousseau and you're making it easier, better. Is there any? Could you give any sense of what is the differences in what you did, and did you apply to similar examples? And can you compare the proofs and the transformations, or were it different languages?
Thank you for question. I think in Kuzu's paper there are 2 example transformations. First is constant propagation, and second is monitoring the traces in something. And I think the main difference of Kuzu's framework and ours is that we use the mature part to identify which part should be replaced to effectively reduce the core part of the proof. So it is considered as base case. And for inductive case, I think it is not a core part of the proof. So we should, it is better to eliminate it using the common properties of the transformation. But I think in Kujo's framework, Kujo's framework can work for not effectively work for rewriting role-based transformation. I think that.
So could we go back? Actually, it's on the slide here, but you have this list of theorems that you say that you prove. What's the reason why you divide into action bias and not action bias? It seems to me that one should be stronger than the other, but maybe this is not true. So what? So you did it for a reason. I'm curious.
Action-wise, semantic substitution is semantic substitution which works for every action. It is something like a map function, and non-action-wise is the semantic substitution which does not work as map function. And for action-wise transformation, it is more easier to prove the elimination of induction case, but while proving the same induction cases for non-action-wise semantic substitution, and I failed to prove it because of the I don't know why I failed it, but with the more assumption with matcher and semantic substitutor, we can prove it also for non-action-wise transformation. So the result is same, but the precondition is different. The action-wise semantic substitutor can prove theorems with only properties of semantic substitutor, but for other theorems, it requires a property of syntactic substitutor and matcher analysis. So I think it's different.
So I'm asking, I'd like to ask about the power of this framework. I believe that this framework is complete for the transformations based on value analysis. Is it correct?
For what?
I mean, if transformation is explainable with value analysis, probably you can prove that in this framework.
Value analysis. I think it is more general than only value analysis. In our example, we use liveness of the variables to show the equivalence, correctness argument of elimination, data assignment to elimination. So I think it is not explainable with only value analysis.
I see. Does it scale to more advanced optimizations like the no alias information or some alias analysis, these things?
I believe that we can prove it for the sophisticated analysis, but we do not actually prove it. Yeah.
Well, at least it's a big conjecture that complete all that.
So let's thank the speaker. All right, so next up is Shaq, who will be telling us about symbolic execution and quantum circuits. Once he's set up.
right? Anytime? Okay, so this is joint work with Amr Sabri and Gerardo Ortiz from Indiana. Let's dive right in. So the basic idea is, and we started doing partial evaluation, and we realized we didn't even need that. We can apply the techniques to quantum circuits, and sometimes it just works. And we were kind of surprised. We were expecting to evaluate really small circuits and be a horrible mess. And that's not what we found. So at the heart of quantum circuits are reversible circuits. So we have to start there. So at the top left, we have a reversible gate, all composed of controlled NOT gates. So the plus things are NOT. And so the first gate basically reads the value of A0 and B0. And if A0 and the CX is at the right, if it's false, it doesn't do anything and passes everything through. If it's true, then it does a NOT. And so all of these are controlled NOT gates. And if you have more than one gate line on which you read something, these are Toffoli gates or generalized Toffoli gates. You can take multiple things that you AND together to decide whether you actually do a NOT or not. So the convention, like we write our circuits with the inputs vertical, but then we write our traces with the inputs horizontal. That's just the way people do it in quantum. And so if you take false, true, 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 and you run it through the circuit, you get the first thing, and so on. The neat thing about these circuits is they can be run backwards. I could take the output and go the other way around. And all quantum circuits are, because of physics, that way. Because you can't lose information at the low level of physics. So reversible circuits are super important for all quantum. And the Toffoli gates are super important. Now, most quantum circuits are going to introduce additional gates, in particular the Hadamard gate, here with an H. And what it does is superposition. This is where quantum gets scary. And it takes, for example, false, and it produces, oh, my output is going to be half the time false, half the time true. And because essentially we're in an L2 norm, half is 1 over root 2. Because 1 over root 2 squared plus 1 over root 2 squared is 1. So yeah, these weights, you get square roots everywhere. But basically, it's the uniform distribution over true and false is the way you want to think of it, and a weight. So those top two wires, you end up in some superposition state, which basically says, if somebody tries to look, I'm going to randomly give them one of those 4 values. And what you observe is really, it's truly random after you've done Hadamard. But it's kind of uniformly random, any of those that you don't know. So you go, hey, well, so if you run the circuit, then you get these superpositions. But it's the same thing as before, you just put all the ORs together. And so you go, well, if it's going to be a uniform superposition that says, I don't know what my value is, that's a symbol. Why don't I replace that scary quantum thing by just putting in a letter? So that's what I've done on the circuit here. And now you run it. And my X and Y are true or false, but I know how to do logic symbolically. And so I know how to do and I know how to do XOR, and you run the circuit and there's the answer. And you can see the superposition. In the first 2 lines, we get X duplicated. So we know that the first line and the last line are equal. And this is not random at all. This is what makes quantum work, that you end up entangling things and having equalities between different qubits being pushed through. But here, we're just using symbolics to do the same thing. And we like algebraic normal form. It's just like super basic logic. We know how to do this. We even know how to do it pretty quickly. So, great. Does that get us anywhere? So a whole bunch of quantum circuits look the same. They have two input lines, a whole bunch of vectors at the top, a whole bunch of vectors at the bottom. The ones at the top are all entangled. They're fed in a great big box, which is reversible. You measure the bottom ones, you do a Fourier transform on the top, and you measure that. You see that a whole lot. And the way the reversible box in the middle is usually done is actually, you take the inputs, the x's, and you push them right through. You don't change them at all. You only read them. And you take the inputs at the bottom and you XOR them with an arbitrary function f. Lo and behold, that's reversible all the time. So you take an absolutely arbitrary function and you make it reversible by remembering your inputs, so you can undo it. It's not that hard. But the H here sort of introduces parallelism that lets you run things in parallel, like a whole bunch of stuff. So what we're going to do is we're going to go symbolic instead. But we're going to throw in one more trick. So normally you run your circuits. But if you look at barrier 2, we only measure the bottom. We do stuff later. So, and we know that U is reversible. So what we can do is I kind of run it part of the way, look at some of our outputs, throw them out, replace the other outputs by symbols, run our circuit backwards, and now we're going to get a set of constraints on what the inputs ought to be for us to get back to where we were. And then if we're lucky, those constraints are actually going to tell us what the circuit does. So yeah, that's kind of sneaky, right? We really are using the fact that the circuits are reversible because we're going to run them backwards. Okay, so if you open up your textbook on quantum theory, at the beginning, there's going to be a whole bunch of algorithms with those names. All names of people, therefore they make no sense whatsoever. You just learn to pattern match. Oh, Deutsch created this algorithm. And we're going to talk about 1, 2, and 5, 6. And I'm going to explain them a little bit, because otherwise I'm going to run out of time. So the Deutsch problem is about balanced function. So Boolean function is balanced if it outputs, like on all inputs, the same numbers of zeros and ones. And the Deutsch problem is, given a function, can you figure out if it's constant or if it's balanced? Well, in some sense, it doesn't seem so hard. You just run it multiple times, like twice, and you look. Quantum problem says, can you do it by running it only once? And quantum says, yes, I can do that. The Deutsch-Jürser problem says, actually, you get n bits. Can you solve the same problem? And often, like, so, for 8 bits, there's like 256 possible input values that you could run, and you might need to run it 256 times to figure out, because you need to count up the bits. With a quantum computer, typically you need to run it 5 or 6 times, and that's enough to get you the answer. That's completely crazy, right? What we're going to do is solve Deutsch-Jürser symbolically by running it once, and we're still going to get the answer. The Grover problem is n bits it represents a number, and only one of them is going to give you a 1, like a true. Everything else is false. So normally, if you want to guess a number, you need to run everything because you could be unlucky and then never know. Again, here, we can do it in one go. Shor, the Shor problem is the most famous one. It's where you use quantum algorithms to factor really quickly. So I won't explain all the details, but basically the setup is quite similar. Right. So yeah, that's the setup. And then we wrote a whole lot of code, lots of code, and realized that we were writing the same code over and over again. And I said, okay, let's write some good code instead of just writing a whole lot of code. So you write down some requirements. What should our code do? Well, we had a whole bunch of different representations of Booleans. That's ridiculous. Like we should be abstract over that. Same thing with formulas. We had a whole bunch of representations. Let's make sure a lot of our algorithms can be abstract over that. We don't care. And we need to be able to run forwards and backwards and symbolic and with real values and so on and so forth. And I don't want separate code for all of that. I just want one piece of code to do that. I want to write down my circuit once and then run it all these different ways. Like, why would I have to write my circuits a whole bunch of different times? So like make sure the polymorphism works. Right, some of the problems require oracles, meaning I'm going to specify my Boolean functions in a particular way. Now I need a circuit, and creating the circuits is a real pain. So great, take a textbook, write the synthesis algorithms. There's tons and tons of them out there, but it ought to generate a reusable circuit that works for any representation. So I need to make sure to write my algorithm in a very generic way. Yeah, it can be done. And then if the circuits aren't too big, the things shouldn't take hours to run, and it should be all right. So at some point, you need to optimize a little bit. So can we do that? So for those of you who know finally tagless will be massively unsurprised that I've used it. If you want to be generic over representations of values and you're a Haskell programmer, you kind of pull that out. So 0, 1, not, and is the basic stuff you need. And n-ary and is useful too. And once in a while you want to optimize it. You throw it in the class as well. And we have 4 implementations of that. 1 numeric, 4 symbolic. So 3 symbolic. So it's really useful to have a class for that. For formulas and representing variables in them, we didn't go with a class because we found that it could pretty much never be inferred. And it wasn't useful at all. So we actually made it an actual record. And so here there's like design, right? Which way do you go? It's possible to go either way. You try it out and then you decide, okay, is it useful to have a class or an interface, or just no, like force people to hand it to me instead of have the compiler guess it for me. So 3 implementations. The first unbelievably naive one, our variables are going to be strings. A bunch of ands are going to be lists. And below that, a formula is going to be a bunch of XORs of ands, just monomials, the simplest way you can think of them. And then we don't normalize them when we do stuff. So when you and a whole bunch of stuff, you just concatenate the lists. Yeah, it's great for debugging. It works. It's going to be really slow. You're doing like so much work that is useless here. It's ridiculous. But it took a while for our benchmarks to even notice that we were using the dumbest possible implementation. So once they started noticing, okay, so why don't we use integers to like 0, 1, 2, 3, 4 for our variables, and then our monomials with ands are going to be a set of those, and we're going to keep them ordered. So to combine them, we union those two maps, and then we're going to be smart, and we're going to use occurrence maps for the XORs, because pretty often you get, oh, this monomial appears, oh, it appears again. So XOR of that, they disappear. Oh, it appears again. Oh, no, it needs to come back in. And then taking monomials in and out, in and out, in and out all the time is just, like, for functional data structures, really, really bad. So don't. Just keep a count. And then at the end, if it's odd or even, make it 0 or 1. Much faster. And then I put the compare on the screen because that's very often the bottleneck. A lot of the time is spent actually comparing things, because down below we have a map and inserts and everything, like tons and tons of compares happen. So if you can make that faster, it's better. This was still not quite fast enough, so we went to bitmaps. So we use actual, natural numbers to represent a bunch of variables or ors, and now and is just a bit or. It's fast. Machines like bitwise ors of natural numbers, and we keep the rest. And this was pretty nice. And of course, there's more stuff to go, but it's all like this is the once you have this core idea, the rest of it is straightforward. And these 3 implementations are, of course, instances of the rest. So we can swap them in and out and just compare. Yay. So, okay, first I'm going to give you some results, then some timings. So Deutsch-USA, which is like decide whether it's balanced or constant. Big circuit, doesn't really matter. Let's run it on guessing that it's going to be 0. If it's constant, the formula you're going to get, the constraint between the inputs and the output, is either going to be 0 equals 0, at which time, yes, it was constant 0, or 1 equals 0. No, never is. It's the other one. Even thousands of gates, but you tricked it, it's a constant gate, you get that answer, small. If it's balanced, it looks like other things, constraints on the inputs that say, if that's the case, then yep, that was the balanced case. You know it's balanced if you see a variable in the output. You don't need any more information than that. That's how we tell. In the middle, you see now in red, a great big 6 variable like constraint thing. What is this bizarre thing? It's a cryptographically strong function, which is balanced, but it's really, really hard to tell that it's balanced. And that's one of the ones that comes out, and it just pops right out. Grover, guess the bit. So here it's for 2 to the 4, like 4 bits, and the bits can be 0 to 15, and the constraints are, here's what it could be. But in red is the answer you want. And it's always going to be in the front, and it basically says, say for u equals 6, bit 1 and bit 2, counting from 0 are on, and I have to eliminate all the other possibilities. So I'm going to XOR with a whole bunch of stuff that says it's only that one and not the other ones that also have those 2 bits. And so if you want no bits on, that's the first case, it's the worst possible one. It's false, and it can't be any of the other things, which is why the last one is the simplest. But in some sense, if you optimize and are super lazy, then if you can manage to get the head of this ordered term, you win. So you can do Grover really fast if you're, and we haven't optimized it quite that much. Same thing for Shore. Here is for factoring 15. You're computing a to the x mod 15. Depending on a, you get different residual equations, which give you a different period for the thing that you pass to the QFT. But once you have a period, then that's enough for factoring. So whether I get period 2 or period 4, it doesn't matter. And the equations are small. For factoring 15, there's a circuit with 4 gates that you can hand optimize. If you generate it using the textbook algorithms, you get 56,000 gates. This result is run on 56,000 gates because it doesn't matter. It works. If you try to factor that, you get 4 million gates, and it still works. 4 million gates. Who'd have thought of partially evaluating a program with 4 million statements? Most people would be kind of afraid of that. But it doesn't always work. These work because the period is a multiple of 2. When the period is not easily expressible as a factor of 2, then things go crazy. Talk about that in the end, assuming I'll still have time. Yes, okay. Right, so some timings. Different balance functions at different sizes. For Deutsche Jose, the representation doesn't matter. It's just exponentially slow. It just gets bigger. Like the answers, nope, yeah. Like the log at the top, and at the bottom, it's really 2 to the n that matters. Yeah, this is just exponential. Grover, on the other hand, it really depends on the size of the answer. In fact, I think at the bottom, we went up to 24 bits. We don't have quantum computers with 24 bits, qubits. For U with all ones, we still couldn't measure the time. Like the granularity of Haskell's timing gave us 0. And for the other extreme case, yeah, you can see that curve going up. It's getting bad, worse and worse. And so the answer matters. And different representations, this is where the good representation in green really matters. And bring that way down, lots of profiling. I only have 2 points, but basically it was getting pretty bad. And it was time to not take a super dumb representation to do more and get up to 20 bits or so instead of already at 12 bits taking 25 seconds. Right, so a little bit of complexity analysis. I won't go too fast, but roughly speaking, the first 2 steps are easy. The third steps, you run backwards. The equations in the worst case can be exponentially big. And that's the worst case, and it happens. So there you go. And depending on the problem, sometimes you can inspect the answer. You can inspect the equations, get your answer, it's great. And in the worst case, you have to solve the equations. And that's NP complete. So exponential plus NP complete. Yeah, sometimes this isn't good. What's surprising is sometimes how amazingly well it works. And we don't know, right? Like, we have no pattern that we've detected on when is it good, when is it bad. As far as we're concerned, that's wide open. Right, so yeah, case by case. Sure, we've done more stuff in the paper where we use trits and dits to get the other cases, and you seem to need to go there. And how to choose, don't know yet. So yeah, symbolic is great. And where quantum needs to run multiple times, we run it once. But of course, that's the worst cases, right? Like, this is not magic. But it's kind of magic in some cases. Like, why? So our speculation is there's some quantum algorithms which we really aren't. Right now, we think they are, but they're not. And this gives us a hint of some of them. Look here. Yeah, there's probably a classical algorithm to do it. Thank you.
Thank you for a very intriguing talk. So my shallow understanding of quantum circuits says that these quantum circuits are usually related to some unitary matrix.
Yep.
And-
That
and-
U is for unitary.
Yeah.
Underneath the hood, that's what's going on.
Yeah, I see. So, but in the deep learning architecture, we already have a very various accelerators for matrix multiplications and all the operations. So can you connect them so that we can reuse the deep learning accelerator framework for this kind of simulations?
See, unitary is really, really special because in a higher dimension, it kind of sits on the unit sphere in the complex plane, and you can't go off of that at all. And matrix multiplication is optimized for dense matrices that lie everywhere. So I think the answer is no. Like, it doesn't help. Plus, all of these circuits, even though the denotational semantics is unitary matrices, they're not there at all. They just don't show up. Yeah, the unitary matrices here in the ZX calculus, in QPy, they're just in the semantics. They're not in the programs you run.
It's exciting stuff. How many qubits did you have in the largest program that you?
How many?
Qubits?
Yeah, I think we've gone up to 24.
Okay.
Just because, like, we wanted some timings here. Yeah. Here we run at 24. We haven't tried all of them for, in some sense, well, it's really Shor that needs more. That's really interesting, and the barrier is the base, not the number of bits. We need to know, like, which qubit basis we need to know, which is basically guessing the period in advance, which is cheating. So we're still working on that.
Right. And I have a question about this thing with Shor. So in my class in the fall, I had the students do one of the Qiskit labs where they do Shor's algorithm, and they found exactly what you said. They're running on a quantum computer, of course, but they found exactly what you said, that when the base is 2 to the something, then everything is so much easier. It can scale much more. And so you see the same phenomenon. So did you try something a little higher, like 21 or something that's not 2 to the... It was like...
Well, 21 factors like stink because the period is a factor of 2. It's the period, not...
the period. Okay. So I think that what the people were able to do in my class was 2 to the 6, sure. But if it's not that, then the numbers they can do are much...
Yeah, so we factor 196,611.
Yeah.
And it's super, super fast.
But
that uses right. The thing is that 3 ends up period 2. And so that's why it's one of the known fast examples.
Okay.
Even though it's a big number, it's easy for sure.
So there's one last question. While we take
Maybe this was already addressed implicitly, but the classical timings didn't really relate to how many bits were properly entangled in sort of the simulation.
Yeah, so no, it really depends on the problem and the size of the answer. Not so much, not nearly as much about the size of the input, weirdly enough.
All right. So last talk of the session will be by Rio. Will be telling us about, what's the title of your paper again? She's looking at this just before. So it's about, yes, right. So it's related to the first, to our first talk of PEPM this morning. So it's about generating, making cryptography algorithms run faster, as far as I understand it.
Why did it connect? What?
So maybe try plugging this out. Okay. Can you try leaving full screen?
Okay.
Try to do what you just did. No. Try a different laptop if you have your presentation. So you tested this just before, right?
I have a tested, but
Could you possibly present on someone else's laptop? Just copy the file.
yes.
There was this slide here from someone. Just copy over. Please.
Okay. Copied. Yes.
Just
Ah. Thank you.
Okay, good. You go to Finder. Yes. Yeah, it should be coming. Let's see. Firing. Give it a second. Okay.
Okay. Okay, so let me start my presentation. So hi everyone, I'm Ryo Tokuda. I'd like to talk about our work on applying program generation and verification to cryptography. I'll begin with an introduction. Our target is cryptographic implementation. What is needed for cryptographic implementation? Traditional cryptography such as RSA and elliptic curve needs high performance. The implementations are based on mathematical algorithms and tricky low-level optimizations are applied. And correctness is also needed. We have to take care of algebraic properties and reasoning about low-level code. So in this case, formalizing all in a proof assistant such as Coq works. How about post-quantum cryptography? The same as the traditional one, the quantum resistant cryptography based on learning with errors problem needs high performance and correctness. In addition, maintainability and extensibility are required. Many experts have proposed combinations of optimizations to compete. Then so the implementation has been updated frequently. Furthermore, new architectures should support these implementations. Therefore, formalizing all may not work in post-quantum cryptography. Program generation techniques can solve this problem. Program generation can cover high performance, maintainability, and extensibility. We can generate and maintain efficient code by using program generation. And Masuda and Kameyama proposed a method that unifies program generation, analysis, and verification. Thanks to their work, the correctness of the code can be assured. This work advances Masuda and Kameyama's work. And Masuda and Kameyama generated NTT code, which is a component of a cryptographic implementation. In addition, they found a new optimization. So in this work, we have found more optimizations and proved that our code is the most optimal. For correctness, they verified the generated NTT code. Similarly, we have generated and verified polynomial multiplication code. Before going into the details, let me give background on cryptography and the tagless final embedding. For key establishment algorithms in post-quantum cryptography, most finalists of the candidates are based on the learning with errors problem. In this algorithm, the polynomial multiplication is performed. its order is n log n. So it's a computation heavy part in the cryptographic implementation. Let me explain the details of the polynomial multiplication. Two polynomials fx and gx are given, and the NTT is applied to each polynomial. After element-wise multiplication of the result, the inverse NTT is applied. The result is the desired product in cryptographic implementation fx gx modulo x to the power of n plus 1. NTT is number theoretic transform defined as shown here. Here, omega n is the nth primitive root of unity. One may ask, is NTT just the discrete Fourier transform? The answer is yes, but it's for values in ZQ. For example, when Q equals 12,289, 13,000 is congruent to 711 modulo Q, so these two numbers are treated the same. Masuda and Kameyama and this work use the tagless finite embedding. It's a way to embed a typed DSA into a meta language. This is realized as follows. An interface defines the typed syntax for embedded DSL. So this is an example of a DSL program and has a type DOM. An interpretation instantiates the interface by defining semantics for embedded DSL. By giving this interpretation, we can execute the DSL program. Let me present other interpretations. We can realize the code generator by using tagless finite embedding. By giving this interpretation, the type DOM is instantiated as a string that represents code. We give this interpretation to realize interval analysis. This instantiates the type DOM as a product of int and int, which represents the lower and upper bounds of values. The inserted assertion checks if the upper bound causes the overflow. In addition, this interpretation realizes a formula generator. We can generate mathematical formulas for the result of the DSL program. In this work, a DSL program is instantiated in some ways as we have seen. The first is code, the second is an interval for analysis, and the third is a formula for verification. From here, I talk about our work. The first work is the analysis-driven optimization. This is the Curie-Tukey algorithm which computes FFT. In NTT, the modulo Q operation is performed many times and it's expensive. For efficiency, tricky low-level implementations. For efficiency, the code is realized by tricky low-level implementations. One example is this byte reduction. It realizes modular reduction by subtracting a multiple of Q from the input. It means that this reduction returns a value congruent to the input modulo Q. So the code is also tricky in the sense that byte reduction is used for U plus 2 times Q minus T. In addition, Montgomery reduction performed after multiplication is even trickier. You may not understand the meaning of this implementation. So as you can see, the correctness of the code is far from obvious. Both high-level algebraic reasoning and low-level reasoning are required. And furthermore, the code is correct only for particular parameters Q and N. However, Masuda and Kamiyama successfully generated a shimmed-optimized code for NTT, which outperforms New Hope, which is a component of which is a cryptographic implementation. Masuda and Kamiyama performed interval analysis to guarantee the absence of integer overflow. This shows the example of an operation and the corresponding pre- and post conditions. The analyzer holds the lower and upper bounds of the values in a program. The bounds of the first operand of mod, x1 and x2, must satisfy this precondition to be an unsigned 16-bit integer. The precondition for second operand is slightly different. The upper bound must be less than 2 to the power of 14. Then the post condition is similar to the second precondition. In this interval analysis, manual control is needed for two reasons. First, different pre- and post conditions are needed for each operation. As we have seen in the previous slide, we must control these conditions. Second, for some reductions, the standard interval analysis, such as Framar-C, failed to infer the desired intervals. For example, low-level operations such as byte reduction needs exhaustive computation to find sufficiently precise bounds. In our work, we have investigated and re-implemented Masuda and Kamiyama's interval analyzer. We have found that some assertions can be replaced like this. The 2 to the power of 14 has been replaced with Q. Actually, we performed interval analysis for stricter conditions, and the result said that their conditions satisfy. So this result leads to a new optimization opportunity. I'll explain the analysis-driven optimization that we have found. This is the innermost loop of NTT program. By applying code generation, we can obtain this straight line code. In this generated code, a loop for J has been unrolled. Many reductions appear in the generated code, like that byte reduction. And some of them can be eliminated as long as there's no overflow. Since the number of byte reduction is related to the performance of the generated code, we should eliminate this as many as possible. By using our interval analyzer, we found more precise bands than Masuda and Kamiyama's interval analyzer. From this, we have found that we can eliminate 69% of reductions. It can improve the performance of the generated code. Please see our paper for more details. In addition, we have checked the optimality of the generated code. We tested all possible codes with fewer reductions, and all of them caused integer overflow. So by applying this approach, we have confirmed that our code is the most optimal in such space. Next, I'll describe how we have proved the functional correctness of the generated code. Our goal is to verify the functional correctness. In other words, it is to check that the generated code satisfies the definition of polynomial multiplication. We have done this with end-to-end verification. Following Masuda and Kamiyama's work, we have decomposed the verification problem into low-level and high-level parts. The low-level parts is verifying the implementations of modular arithmetic. The high-level part is verifying the DSL program. Here, we assume the correctness of the low-level part. So let me explain the details of each part. First, we need to verify the functional correctness of the low-level implementations. For example, the input and the output of byte reduction must be congruent modulo Q when the input is an arbitrary unsigned 16-bit integer. So there are two ways to verify it. Masuda and Kamiyama used an SMT solver. On the other hand, we used a brute force approach. It applies the reduction to all possible inputs and checks if the results satisfy the specification. We have verified all three reductions in the code in only 1 minute. So we have verified the low-level part, so all low-level implementations can be replaced with normal modular arithmetic operations. Assuming it, we can verify the high-level part, whether the result of the executing the polynomial multiplication code is equivalent to the definition. In normal execution of the polynomial multiplication program, both the input and output are concrete values. We have replaced this normal execution with formula generation to make the input variables and make the output formulas. Next, we have compared the generated formulas with the definition of polynomial multiplication. We have checked that the generated formulas are congruent to the definitional formula modulo Q. This verification succeeds, and it takes about 6 minutes for formula generation and 6 seconds for checking. Hereby, the functional correctness of the generated code has been verified. There are many related works, and I'll introduce one of them. Wang and others proposed a method for complete verification. They verified various efficient assembly code with a verification tool called cryptline. their method needs human effort to insert assertions. So it's more reliable but less extensible, and it's probably not suitable for frequent updates of the code. In contrast, our method is lightweight verification. It relies on a bigger trusted computing base than their method, but however, we have verified modularly, so it's easier to extend and modify. It's good for exploring new optimizations. So let me conclude this work. Our contribution can be summarized in 3 points. The first, we have proposed a method to generate polynomial multiplication code. Second, we optimized the generated code and showed the optimality in a search space. Third, we analyzed and verified the generated code in a lightweight way. Future work includes applying this method to other implementations for post-quantum cryptography, such as Crystal's Kyber. We also consider generating and verifying optimized shimmed code as our future work. Thank you for listening.
When doing NTT in the multiplication operations and the Montgomery reduction, you're multiplying by a pre-computed constant. Is that correct? And if so, can you optimize the multiplication because you know the constant?
Sorry, one more time.
So when doing the multiplications inside the entity, you're multiplying by constants from a table. Is that correct?
Yes.
Yes. So how do you optimize the multiplication based on the values of the constants, or do you treat them as opaque?
I used one particular constants for the NTT program, and but we believe that we can this method can use the another parameters, and similarly we can generate and verify the code. So we think the constants for the entity doesn't matter for the our method.
Thank you.
Thank you for presentation. And I remember that in lower level part, verification of lower level part, it use brute force, so it consumes 60 seconds.
Yes.
And does it grow larger when the parameters of the Q or N grows, or it is constant?
Yes, it's constant.
Thank you.
Is there burning final last questions? Then I suggest we wrap up the session by thanking Rio again.
I believe there's lunch upstairs. Is that also that lunch is upstairs? Follow the signs or follow